Okay, we're up, we're live. What are we working on today? Anything new come up over the week? Looking at module 4. I think last couple of classes we were talking about like Gauss elimination, like where errors, both error in terms of like accuracy of how well you can solve problems is, and then also errors that can happen of like if you're creating your own Gauss elimination process without partial pivoting, then you can end up trying to divide by 0 to like solve the problem. It's not a huge issue. Most solvers like linalg, the linalg solve, and even this LU decomposition process uses some kind of pivoting, so it avoids a lot of those issues. Is anybody working on revisiting linear regression yet? Not yet. Oh, okay. All right. I won't jump like too far ahead if we're not there yet. But linear regression is called linear regression not because it's always straight lines, but because it's a linear algebra problem. Pretty nice when things work out that way. Just chugging along. All right, let me check in, see where we're at. If there's anything that I can do that might be helpful or interesting, I'll jump back up and try some demos. Yeah. Just getting going. Yeah. Where are you guys? Okay. Looking out Gauss elimination, LU decomposition. Yeah. Okay. Okay. Nice. Using that to solve LU. Yeah.
Yeah, so uploading the file for the last problem, the DAT file, it's giving me an error basically saying the header is not, can't convert string float to the header's time.
Oh,
how do you get around that?
so this,
Because I'm using low text.
yeah, load text works.
You just do skip rows.
Yeah, we can use skip rows though. So coming down here, just running everything. So I've got everything loaded in. And, all right. So if you're trying to load data from either a DAT file or a CSV, like any kind of like structured format, this is typical for like Instron machines and all sorts of. They give you structured data that you can read, that the computer can read, but sometimes it's hard. Sometimes it's hard to like troubleshoot how you're supposed to read it in. This is my process for like figuring it out. One way is you could like open it up in Excel and then look at the thing. I like to just look at the raw text to figure out how can I tell Python how I want to load this in. And that's why I like that head command, use that bang operator, the exclamation point. And when I look at if you load it up in Excel, it's going to show you like 0 and 38 in two different columns, and time and stress in that first row, first two columns. But here I can see like, all right, it's definitely comma separated. So if I tell Python load it in based on commas separating the values, and that's good. And I don't need the first row. So that's like the two things that I'm trying to tease out. It's like how many rows are information and then the rest of the file is all that structured data. So now I can say load text of that same file that I just figured out where it was. I can tell it my delimiter. Let's do multiple rows. My delimiter is a comma, and also skip rows. I'll skip that first row so that it ignores time and stress and only gives me the numbers. And now I've got like a nice structured array, time 0, 38. time 54 seconds is 33. And because I looked at the data file, I know time is in seconds, stress is megapascal. So that's my process, is always like look at the raw like text that I'm trying to load in, and then use that to like tell Python how to read that data in there. All right, other thing that we were kind of taking a look at was backing up to here. Let's copy this. And then copy. Do I have a plot here? So I just wanted to compare like stuff that I'm solving for. So on this axis, this is F in newtons, and this is P1 in newtons. So if there's zero force, then there's no internal reaction force, and the more I'm pushing down. So right now, yeah, theta equals 0. So I'm not pushing at an angle, I'm pushing straight down like that. So if I'm pushing straight down, then there's no external left or right reaction force. So this R1 is 0, and then R2 and R3 are both positive. They're both going to be F over 2. In that positive direction. And then the way that I drew these internal forces at each like connecting point, they're all describing compression. So a positive number means that I'm compressing like bar number 1. So if P1 is positive, then the whole bar is like getting squished. But in this case, it's negative, which means it's pulling on the bar like that. And the bigger the force that I push down, the more it's stretching that bar out. And that makes sense for this problem. It's always good to like do a sanity check on if I'm getting this result. Is it real? It makes sense. And the fact that it's like 10 times less. Does that make sense? I think so. It seems to make sense. Because there's no, that P1 is only holding like the thing, keeping the thing from collapsing down. So there's not a lot of internal force needed for that triangle. That's why we use triangles for bridges and trusses and all sorts of stuff. Because you don't need a lot of like cross member stress, a lot of like cross member tension to hold stuff up. what does it look like? Do we have this one written out? Yeah, we do. Take these out. And then what do we want? We want P1, so it's still just X0. So now changes the slope a little bit, and theta here is going to be pi over 4. So it's pushing it at a 45-degree angle, but we still have, and again, kind of makes sense, like a negative number. So this thing, it's not pulling things together, it's getting pulled apart. So negative means that P1 is actually looking like that. Seems to make sense. Cool. Anything else going on?
Yeah. Question on compression.
Yeah.
If you go to the third module, I'm not sure, third lesson.
Yeah.
In module 4.
In here?
Yeah. So when you're going to create kind of the first thing, you're going to create the Z matrix.
Yeah.
And you're doing the NP block function.
Okay.
I get what that does. It concatenates all those things.
Yeah.
It's doing it in the reverse order of what was shown in the example above. So if you just go down
Yeah.
a little bit. You see it describes the Z matrix starting with 1 and then x1 and then x2 squared.
Oh yeah.
And
yeah.
then when the Z matrix is created below, it's doing it x squared, then
X squared,
then x1 0.
Yeah, that's true.
So it doesn't matter, right? As long as when you plot it, you're multiplying, because the coefficients you're going to get will now be reversed, basically.
Yeah.
Right? The first coefficient is going to be the x squared term.
That's true.
But as long as you're plotting it that way, it doesn't matter.
Yeah.
Right?
Yeah. So like when we use polyfit is setting it up in the reverse, where polyfit sets it up this way, where the highest polynomial term comes first and the lowest comes last.
So just what was shown above is just reverse of that, basically.
Yeah,
where
yeah, it
the
is
lowest
the
to highest.
reverse. Yep.
So as long as you know that it's going highest to lowest, because eventually it spits out the coefficients A at the bottom. You
Yeah,
just have to know that the first one is the highest order.
exactly.
Okay.
Yeah. Yeah, so when we solve this problem of like A equals all that stuff, like the linear regression formula, then this is our coefficient for like the x squared term, and then this one is for slope, and then the last one is like initial value, like intercept.
Yeah. So when we're going to do the homework problem, are we just assuming it's essentially a second order polynomial because of how it looks, or does it solve for, because we have to set up the Z matrix?
I don't think we're doing any polynomial fits here.
Or it's the least squared regression, I guess.
Yeah.
That's for the Z matrix for the least squared regression. And
Yeah,
so
like
when we created the Z matrix in that other example, you knew it was, x squared was your highest term. Are we just assuming that's the same thing here?
So in this case, we don't have any like x squared. I mean, unless you're considering like e to the t as a polynomial, as an infinite series of polynomials, but really we're using like e to the something as our z processor in this case. Yeah, and this one is also polynomials, but like in this case we're using, there's like sine wave kind of stuff. Like we know it looks like sine waves, we just don't know what the total amplitude of those sine waves are.
Then how do you go about making your Z matrix if you don't know that it's a simple, second degree polynomial?
You make it the same way. So it's like in this case, I'm making Z as sine of t and sine of 3t, where my first column is going to be order, like just frequency of 1 radian per second, and then the next column is 3 radian per second. And now, SM, I gotta load in my, there we go, stats models.
So
that was the problem.
So then for the homework, instead of, sine to the t and sine to the 3t, we know it's e to the minus something t.
Yeah, exactly.
So
yep.
You would block those all together and transpose it, right?
Yeah.
Okay.
So like when I end up getting the result here, it matches. I mean, part of it is like I created a sine wave and gave it some error, and then refit it to it, but it fits really well, and we get those two amplitudes of like 1 volt and then also half a volt. But those are the two, like, and this is kind of like most people would do this with a Fourier transform, but roughly you could do Fourier transforms with linear regression. Then is there another one? Yeah, and same thing here, where I'm gonna have a linear term, a t to the 0, just a 1 term, and then also like a heaviside function multiplied by my slope. So at 1970, it's going to change the slope by, so it will only have values after 1970. So 0 up until I get to here, and then it starts 10, 20, 30. And when I do the fit, then I end up with a nice like piecewise, and it's connected. We don't have that same problem that we did in the second module where every time you do a piecewise fit, like has like C doesn't have C0 continuity. So the slope is different and the connecting points are different. Here we can keep it all as one thing. Yeah, and this, so it's and again, I like to write this stuff out because it helps me think about it. So when we write out this equation of like, all right, I have measurements of stress, and this is my function. I want to take all these functions of t, and they all have different amplitudes, and I don't know what those amplitudes are. I can pull out those amplitudes into some unknown a1 through 5. Like these are all the coefficients that I'm trying to solve for. And then everything else is just some function of t. And that function can be whatever we want. I could throw polynomials in here. Mainly, I don't want to overfit things. So in this case, it makes sense to use these time constants because that's the things that they, at least in this study for this weak kernel, that's the time constants that they expected or that they were looking to fit. So my Z matrix is going to look like e to the 0 is all going to be 1, 1, 1, 1, 1. And then at like 1, e to the negative 1 over 1.78, e to the negative 1 over 11, 1 over 53. And then that one's still just 1.
We have an error on the last term in the matrix, the Z matrix, because it's not the same dimension. Because the first 4 dimensions are length of 22, because there's 22 time values.
Yeah.
And the last one, if I just put in, e to the 0, it's a constant, it's just 1.
Oh, yeah.
What's
so
the way to get, what's the best way to get around that? Is just do t to the 0?
Yeah, you can do t to the 0.
T times 0, something
yeah.
like that.
So if I wanted to say, oh yeah, I should. T over 1.778. And I'll just do like first 2 terms. So if I want to keep it like all in the same form, I could say exp of t times 0. So take every value of t, multiply by 0. Or you could say like t to the 0 is going to give you 1.
It works.
Yeah. You can also say like np dot ones of length of t. And that would, let's see how that one. Doesn't like it. Oh yeah. Make sure we have the brackets all matching up. And they're just taking like the first two time constants, end up with e to the negative t over 1.8, and then e to the negative t over 11. And then the last column's all ones, just to get like an offset kind of coefficient. And I think at one point, someone was asking like, how do I get the r squared parameters from polyfit and all that? Like if you're looking for more stats information, this SM, the stats models, gives you a lot more. So like if I look at the full output of results when I do a model fit, oh, what's your problem? That's the parameters that I get, but then, oh my god, what is the, maybe summary? There we go. So if you look at the results summary, whenever you use stats models, gives you all sorts of great like stats information about how do I know that this was a good fit, like overload with like number of observations 100, degrees of freedom 98, degrees of freedom of my model was 2. Yep, all sorts of good stuff. Here's like the r squared value. That's the one that when you're doing linear regression, r squared, you want it to be close to 1, but if it's exactly 1, then you're probably overfitting. Anyway, get all that good stuff there. Oh, data is not defined. Oh, okay. So it's not that it was so when you load that load text, the only missing part is you can say data equals that load text, and that'll define a new variable called data. before n like a equals, so the variable is, so that output field text is the variable data. So delete your text now, and then forward slash that. The forward slash just lets you like continue programming on the next line. Okay. Yeah, it's as if you put it all on the line. Yeah. If it's in parentheses, then you can use as many lines as you want. But if you're just trying to like write multi-line script like that. Yeah. Nice. This year. I don't know why. Yeah. Thanks. Yeah. Yeah. Now it's all that. Oh. So then the next yeah. Okay. And that's that. All right. Right now, you're taking that function value each point. You want to create new ones. You create a C eval, which is the same exact thing. Instead of from data set. Yeah, I can show you.
Question, I think I was already talking about that, but I got the best fit line, but it asked for 50 data points, not
Yeah,
22.
okay. That's what I was just gonna take a look at. All right. So we have our data. We are creating this Z matrix. I guess I have to write out the next ones. T over T over 53 NP exp of negative T over 411. And then and we could do either one, but one way is to load in my stats models. Then create like an ordinary least squares from stress and Z. Oh yeah, let's do this. So I like to, this is my own like personal preference, but if I have discrete data, like measured data points or like numerical integration, I like to put markers to say like, all right, I don't have anything in between these data points. Maybe I can interpolate between them, but so that's what I like to do, is show if it's a smooth line, then that's something, it's a function that either I made or it's a best fit function. But if we're trying, so right now this like Z at A, if I look at like length of that, there's only 22 data points from 0 to 600, because I'm only evaluating the function at those points in time where I measured stress. But I have like a general function now. I can evaluate it for as many time data points as I want. If I want to do that, I could take this same Z, let's like copy it down here, and instead of T, I'll call this like T function, something like that. Just a new value of time where I'm going to choose how many parts I want to. So my Z function is going to be all whatever T happens, whatever that T function happens to be. And we're going from 0 to 600. And if we want I'm going to say like 51 data points. So every 600 over 50, it's going to evaluate at each of those points. Oh,
the A range. Lin space. What is lin space? The third input. How many steps there will be?
Oh, it tells you how many. For lin space, it's a start, stop, number of steps. Okay. Yep.
A range is the step.
Right? Yeah. So now instead of Z times that A, I'm going to use that Z function times A. And I set it up exactly the same way as my Z value. It's just, and I should probably use my T function like that. And it doesn't make a huge difference because it was pretty smooth before, but now I have 51 data points in there, so a little bit smoother looking. That becomes important, especially if you're using like high order polynomials to fit through data, because sometimes the polynomial does crazy things to minimize your R squared. Like the error at that exact point is small, but in between it's like flip-flopping up and down. So in here, like if yeah, let's say that. Let's go 7, 5, 3, 1. I guess we're out of time. Messed it up. All right, I'll get there. We'll get there. I'm messing up my my brackets and parentheses somehow. Okay, anyway, have a good weekend and see you again on Monday. What did I do wrong? How did I break this? Thanks a lot. You too. Thanks, you too. Broke it. Thanks a lot. Thanks. All right, now I gotta get this. Gotta finish. What am I doing? That means somewhere. That one's good. That's good. That's good. That's good. There we go.